everyone, my name is Chuan. Today it is my great pleasure to present our work at CP2021. This work is about set solving. In particular, we propose a construct and cut method for improving the initialization stage of stochastic local search set solvers. The title of our presentation is Improving Local Search for Structured Set Formulas while Unit Propagation based construct and cut initialization. Let's start. First of all, let me introduce the Boolean satisfiability set problem. Given a set of Boolean variables, each variable can only take Boolean value, either false or true. Based on those Boolean variables, we can obtain a set of corresponding literals. In particular, a variable or its negative form is a literal. Then we can use literals to construct a set of clauses, as shown in this slide. Actually, in the set problem, a formula is usually expressed in conjunctive normal form CNF. An example of CNF formula is presented in this slide. Given a CNF formula F, the Boolean satisfiability problem is to test whether there exists an assignment of Boolean values to the variables in F, such that F evaluates to true. The set problem is very important in both theory and practice. In theory, set is the first problem that proves to be NP-complete. In practice, set solvers have presented great success in many real-world applications, including bounded model checking, program verification, and mathematical theory proving. Practical methods for solving set can be mainly divided into two classes: complete methods and incomplete methods. For complete methods, conflict-driven cross-learning CDCL solvers are mainstream. CDCL solvers evolve from the DPLL backchecking procedure and combine reasoning techniques. It is well acknowledged that CDCL solvers are very successful in solving application set instances. For incomplete methods, stochastic local search, SLS, is the most popular one. SLS solvers can efficiently find solutions for certain types of application set instances, such as station repacking and mathematical problems. Also, SLS solvers are usually much simpler and lighter than CDCL ones. Indeed, local search has proven to be very effective in solving many NP-hard combinatorial optimization problems. However, it is known that SLS solvers are not effective as CDCL solvers on solving structured set instances, particularly those from real-world applications. In this slide, we briefly introduce how stochastic local search solvers work when solving set instances. As you can see from this slide, SLS solvers consist of two stages: the initialization stage and the search stage. In the initialization stage, SLS solvers aim to generate a complete assignment as the initialized assignment. For the initialization stage, most SLS solvers use random strategy for initialization, including CCANR, proper set, and set time. Also, high-performance SLS use greedy strategy for initialization, such as Jian. In the search stage, SLS solvers start from the generated initialized assignment and iteratively flips a variable to search for a satisfying assignment. The entire SLS framework for set is illustrated in the figure located in the right-hand side. As you can see, the initialization stage generates an initialized assignment and hands it to the search stage, and the search stage tries to find a satisfying assignment. Here, we discuss how to improve the performance of stochastic local search. Actually, most existing research works focus on enhancing the search stage, which results in a number of achievements, such as work set like variable selection, clause weighting scheme, permission decreasing variables, probability distribution-based selection, configuration checking, and so on. In the context of SLS for solving set, the initialization stage is ignored. As discussed before, SLS solvers usually use very simple initialization methods, such as generating initialized assignments randomly or greedily. However, good quality initialized assignment might lead to performance improvement. As a result, in our paper, our target is to enhance the initialization stage. Now, let's rethink why CDCL solvers perform much better than SLS solvers on real-world problems. The main reason is that, different from SLS solvers, CDCL solvers use reasoning techniques, such as unit propagation (UP). Also, it seems that real-world problems like reasoning. Let's think about how we human beings solve real-world problems. We first make some decisions, and then figure out some intermediate results. After that, based on those intermediate results, we make some decisions, and go on. Actually, through this way, the solutions are consistent with themselves in many parts. Besides the power of CDCL solvers, we also need to rethink why SLS solvers does not perform well on solving real-world problems. What's wrong with the stochastic local search? The possible reason is that SLS solvers do not consider relationship among variables. As a result, a promising direction for improving SLS solvers is to incorporate reasoning techniques, such as UP, into the initialization stages of SLS. Actually, UP has been applied to SLS solvers before. Thus, how do existing research works apply UP to SLS solvers for set? Some Propagation works adopt UP as a preprocessor, such as unit work and Xindi. They use UP to simplify the given formula, and then call SLS solvers to solve the simplified formula. Different from unit work and Xindi, other works call UP when local optima is encountered, such as ego UP. Beyond that, UP has been used in SLS solvers for solving the maximum satisfiability maxset problem. For example, our previously proposed SLS solvers for maxset, including dist UP, CCEHC, and DZLS, make the use of UP-based initialization. However, in the above works, the initialization does not use any pruning techniques. Now, in this slide, we propose a novel UP-based construction and cut CNC method for initialization. The procedures of how CNC method works are illustrated in this figure. We also describe how CNC method works as follows. The CNC method iteratively performs assigning procedures. In each construction try, CNC starts from an empty assignment and extends it to a complete assignment. Then, CNC method would evaluate the complete assignment's quality. Particularly, the number of empty clauses is used as the cost of the complete assignment. After a construction try is done, CNC method maintains the current best cost as upper bound, and provides the upper bound as well as the variable assignment order to the next construction try. In the following construction tries, if an assignment cost exceeds upper bound, then CNC methods identify the corresponding construction try as unpermission try and cuts the unpermission try. Finally, CNC method outputs the assignment with the best cost. After introducing the technical parts of CNC method, in this slide, we introduce how to integrate CNC into SLS. The combination of CNC and SLS works as follows, and illustrated in the right-hand side figure. In step 1, CNC method is first called to produce an initialized assignment alpha 0. In step 2, SLS use alpha 0 as its initialized assignment and conducts the search to optimize alpha 0 with a search step limit. Then, the framework repeats step 1 and step 2 until time limit is reached. Once terminated, the framework reports the best solution found so far. Actually, our CNC method is a general method, since in theory, CNC method can cooperate with any SLS that originally used random initialization. In order to evaluate the effectiveness of CNC, we adopt 3 benchmarks. The first benchmark is FCC, which contains nearly 10,000 instances collected from the project of spectrum reparking. The project is conducted by US Federal Communication Commission, resulting in $7 billion revenue. The second benchmark is PTN, which includes 23 instances, encoded from a long-term open mathematical problem. The third benchmark is SM5, which consists of 6 instances, encoded from a mathematical problem called Shaw number 5. This mathematical problem is a century-old mathematical problem. In this slide, we introduce the solvers we used in our work. First, we introduce the SLS solvers used for combination with our CNC method. There are 3 SLS solvers, and they are CCANR probe set and set time. Then, we describe the SLS solvers used for comparison. In particular, those SLS solvers utilize their own specific initialization techniques. They are YASET and unit work. Finally, we list the CDCL solvers for comparison. They are Maple Com SPS, the winner of Mantrack of Set Competition 2017. Maple LCM Dist, the winner of Mantrack of Set Competition 2018. Catical, which solves the most instances in Mantrack of Set Competition 2019. And KeySet, the winner of Mantrack of Set Competition 2020. In this slide, we present the experimental results of comparison against SLS solvers. According to the results, it is clear that CNC method is effective, since CNC method is able to improve the practical performance of SLS on all 3 benchmarks, including FCC, PTN, and SM5. Also, CNC method is general, since it can enhance the practical performance of all 3 solvers, including CCANR probe set and set time. Also, CCNR equipped with CNC method significantly outperforms Jian set on all three benchmarks. Now, we switch to the experimental results of comparison against CDCL solvers. It is clear that CCNR equipped with CNC method significantly narrows the performance gap between SLS solvers and CDCL solvers on solving application set instances. In particular, on FCC benchmark, CCNR equipped with CNC performs worse than the set version of KitSet, but it achieves better performance than all other CDCL solvers. On PTN and SM5 benchmarks, CCNR equipped with CNC performs better than all CDCL solvers. Since PTN and SM5 are graph coloring related set benchmarks, it seems that CNC method works quite well on solving graph coloring related problems. Here, we summarize our work. In this work, we propose an effective method called construct and cut CNC. Our CNC method generates initialized assignments for SLS solvers for solving set. Our proposed CNC method is both effective and general. CNC is effective since it leads to performance improvement on all three benchmarks. CNC is general since it is able to improve all three SLS solvers. Our proposed CNC method can achieve good performance on certain types of application set instances. Actually, SLS solvers equipped with CNC method shows effectiveness in solving three application set benchmarks, including FCC, PTN, and SM5. Thanks very much for your attention. That's all.